This video is on writing nuclear reactions. So the previous video talked about nuclear reactions and why they occur. And this is showing how you would write them given just asked to write an actual reaction. So for nuclear reactions, the mass number and the nuclear charge must be conserved. So this is our conservation of energy for nuclear reactions. They can either have emission or absorption of nuclear particles. So that's at transmutations. And we want them to have their nuclear particles either absorbing them, so they're taking them in, that would be one of the reactants, or if they are emitting them, they'd be giving them off and they would be one of the products. So example number 1 has you have sulfur, and sulfur is decaying, and we don't know what our particle is here, into a beta particle. Okay? Because our beta particle is on the product side, we know it's beta emission. We're given the mass number of 32 in sulfur, so we can pull off our periodic table the atomic number, which is 16. Okay. We need our mass number to be conserved. So to have our mass number to be conserved, we need to have 32 on the left-hand side, 32 on the right-hand side. We have 0, so 0 plus 32 is going to make 32 on the right-hand side. On the left-hand side, we want an atomic number of 16, because that's given to us because we have sulfur. So on the right-hand side, we need our 2 added up to also be 16, which ends up being 15 and, oops, let's fix that. We need it to be 17 and negative 1. (17 and negative 1), which actually is not phosphorus, but it is chlorine. Okay. So now we have this written, everything's balanced. It's one thing to watch with your negative 1s to make sure that you are adding them appropriately with that negative number. Okay. To translate this into words, we say that sulfur 32, that's our isotope of sulfur we're looking at, given by our mass number 32 there, decays into phosphorus. This will now be chlorine, right? Because we need to change that. So chlorine changes to chlorine 32 via a beta emission because our beta particle is being emitted, given off. Okay? Skipping down then to example number 2, we have oxygen is going to decay into our nitrogen plus some kind of particle is going to be given off. Okay? We know that we have oxygen, that's atomic number 8. Nitrogen is atomic number 7, so we can fill those in. Well, my mass number doesn't change here. It's 14 to 14, so I know my particle I'm adding has to have a mass number of 0. Okay. I need my charge to be 8, and currently it's 7, so I'm going to add one more. So now I have 0 plus 1. Well, that is my numbers for a positron, which I abbreviate as an E. Because my positron's on the product side, this is a positron emission, and I can write that out as oxygen 14 decays via positron emission, giving off its positron, to nitrogen 14. Example number 3 gives you plutonium 242, decays into, we want to just add a 2 here in front of my helium, which is really my alpha particle. So if it decays into 2 alpha particles, what is its other product? Well, again, my mass number needs to be conserved, so 242 on the reactant side. That is 4 times 2, which is 8, plus 234 is 242. And then my charge needs to be conserved as well. I have 94 in my reactants. I have 2 by 2, that's 4 here, plus 90 is 94. So 234, 90. Well, 90 is the atomic number for thorium, and that is TH. Again, here, my type of actual nuclear decay is via an alpha emission because I'm giving off an alpha particle. And in fact, here I'm giving off 2 alpha particles. So when I write this out in words, I said I have plutonium 242 is going to decay to thorium 234 via emission of 2 alpha particles. So not just 1, but 2 in this case, because it needs to be balanced completely.